Hi, this video we're going to look at polar moment of inertia. We have learned about moment of inertia in the previous videos, and polar moment of inertia is more involved in cylindrical shaft, or tubes. Okay, so the governing equation is J. J is polar moment of inertia symbol. It's equal to R squared dA, and R is going to be right there. Okay, and then if you look at this Pythagorean theorem, R squared is going to be equal to X squared and Y squared. So if you plug that in there and distribute them, and we learned S squared dA, that's going to be our IY, and IY integration Y squared dA, that's going to be our IX. So you got this important information. This polar moment of inertia is going to be equal to Ix plus Iy. Okay. All right, now let's look at actually the cylindrical shaft. If we were using this formula of, R squared dA, so we start with R squared dA. And then the way we're drawing our differential area is no longer a rectangular strip. In this situation, it's going to be whatever you see, this black ring here. That's going to be our dA, this donut, right? And how do we describe this dA? It's hard to figure out the area, but one very quick, simple thing, you're actually going to use it later on in your engineering curricular classes, is if you imagine you have a scissor, you go ahead and cut it open and you unroll this is going to become a very thin rectangular strip, right? If you unroll and straighten it, it's going to be basically a rectangular strip. And what's the length here? The length here is going to be the perimeter or circumference, which is 2 pi r. And our r here, they are using u. Okay, u is going to be the radius. And then this differential element, that's going to be our du. Basically, it's differential element of the radius du. Now we figure out this dA. It's going to be 2 pi u du. So plug that into this equation right here for dA. Then we have r squared. This r is actually u here. They're using u for radius. Then 2 pi u du. And then when you integrate, 2 pi taking out, and then you have u cubed inside, and then become u fourth, right? So it's become 2 pi u fourth over 4. And remember, this u, this radius is changing from 0 to this radius of the circle. This r here is not a variable. This r is a constant, right? That's the radius of the circle. However, u here is basically a variable, and u is changing from 0 to r. All right, so once you get all that, then you go ahead and solve it. So this is a very important equation. J, polar moment of inertia for solid circle, is pi over 2 r to the power of 4th. Okay, now remember we learned J is summation of Ix and Iy. And for circle, regardless Ix or Iy, they should be the same because it's symmetric. So in that situation, your Ix and Iy, they are equal. Oops. And they are going to be equal to half of this j. So that's going to be pi r to the 4th over 4. So those are the two important equations. All right. And one more thing I want to add to, imagine if you are dealing with a tube that's have an inner circle and outer circle, and those are made of the materials. For example, you have a copper tube, and the hollow part is where the fluid is passing through. Then imagine if we know this is outer radius, RO. Then we have the inner radius, RI. Okay, so in that situation, if you want to find this J for this hollow tube, then we're going to have this formula. It's going to be pi over 2 r to the fourth outer minus r n to the fourth. The way we did it is we basically said this entire thing is going to be equal to this outer one minus this inner one, right? This outer one is RO, the inner one is have an inner radius I. So that's it. That's how we got for the tube. And you will using this equation quite often as well. Alright, so that's polar moment of inertia. I'll see you next time. Bye.